Alrighty, so here we go, one of the last few lessons of our linear regression unit, and this is about computer output. It's quite common on the AP Stat exam for you to get this computer output and then just have to apply all the interpretations that we've been practicing over the last few lessons. And so this can happen in the FRQ portion, or this can happen in the multiple choice section. Not every year is there a type of linear regression question. It kind of happens every other year, every 2 to 3, things like that. But we're going to take a look at one of my most favorite AP Stat questions, which is from the 2005 free response section. Now, when you see computer output, what's grayed out is not relevant to us yet. In our later unit, we'll talk more about it. But for now, we're just going to focus on these few spots. So our constant is going to represent the y-intercept. Our explanatory variable will be the slope. We'll have the standard deviation of the residuals and the coefficient of determination. From the coefficient of determination, I can also calculate the correlation coefficient. So that's going to be 1, 2, 3, 4, 5 different interpretations there. And because I have A and B, I'll be able to give the equation of y hat, so now I can make predictions and find residuals. And most times they're also going to give you the output. So they'll give you the data, they'll give you a scatter plot, they'll give you a residual plot, and then here's the computer output for us. So what I need you to do is just, for this unit, we are going to ignore these columns right here. For now, they just they offer no utility to us. Also, we will never use the r-square adjusted in this course. We're just going to focus on regular schmegular r-squared, or the coefficient of determination. So now I have all of this information. I've got the 2 graphs that I'll be using. We can actually go ahead and just work through this problem. So you'll be given this output, and here the Great Plains Railroad is interested in studying how fuel consumption is related to the number of rail cars for trains on a certain route between OKC and Omaha. A random sample of 10 trains on this route has yielded the data in the table below, and a scatter plot, residual plot, and the output for the regression analysis are also included. So here's the data that went in. Our explanatory variable is the number of rail cars. Our response variable is fuel consumption, and we have some units here. We can see in our scatter plot that we could say there's probably a strong positive linear relationship, and that'll bring us to our first question here. Describe and interpret the association. So what I need you to do, I need you to pause the video, and I need you to see which of these elements you are able to work through. And I think I gave you like 15 or 16 components. Typically on the AP exam, they're only going to ask for 3 to 4. So you have all your interpretations from the previous lessons to work through this. So what I need you to do is I need you to work through the rest of this section, and we'll come back and review. And it's not really new content, it's just applying what we've already learned and identifying it from this output. So go ahead and pause the video, use your notes, and good luck. Alright, so hopefully not too complicated, but let's go through and make sure that our interpretations are pretty much good to go. So here, I already kind of verbally said it, but here is what it would look like in a written response. There appears to be a strong positive and linear relationship between the number of rail cars and fuel consumption. On average, as the number of rail cars increases, so does fuel consumption. Again, on average. Not always, but most times. Okay, now determining the correlation coefficient, again, I have r squared, so I'm going to take the square root of r, but the sign of r depends on the slope. And so for us, the slope is positive, so my correlation coefficient should be positive. So I just take the square root there. Now I have from the correlation coefficient, I get the strength, which here is strong because it's above 0.8. And I have direction, which here is positive because of the sign of the correlation coefficient. Now, again, to assess the linearity, we need the scatter plot and the residual plot, but don't worry, it's coming up shortly. Now, another popular question is to list the LSRL equation. So again, here I have my constant, which is my intercept, and then the slope is special, so it always gets a name. So here's my A, here's my B, so y hat equals A plus B. And notice that I'm going to define my variables. So x is the number of rail cars, and y hat is predicted fuel consumption. Again, not actual, predicted. Now use our model that we just created to predict a train with the 28 rail cars. I'm going to substitute in 28. Here's my output. Now, if I want to find the residual, again, finding the residual, just the actual minus predicted, AP. But then also, you could just find the residual by using the formula. So here, Actually, here it's the more popular question these days of here's the explanatory value, here's the value of E, here's your error, your residual, find the actual. Manipulating this equation here gives us Y equals the error plus the prediction, and do a little plug and chug, get our answer there. Now, for the slope, usually there's going to be one interpretation. So for each additional rail car added, we predict an increase in fuel consumption by 2.1495 units per mile. Again, just our interpretation with the value in the context. What would be the difference in fuel consumption between the train with 23 rail cars and 32 rail cars? And so this one is not super intuitive. Like if you're like me, you would just plug everything in and then take the difference. But mathematically, some of you might have recognized that here's the form of the first equation. Here's the form of the second equation. A minus A, the intercepts are going to cancel out. So I'm just looking at the change between 32 and 23, which, lo and behold, slope accounts for that constant proportional change between the units. So I can just find the slope or the rate of change between those 2 points, which will give me 19.346. Or if you don't believe me, go ahead and substitute these values in and take the difference, and you should get about the same answer. All right, on to the next, some more interpretations galore. The y-intercept for a train with 0 rail cars, we predict fuel consumption to be 10.677 units per mile. That pretty much makes sense, right? Just because there's no rail cars attached, that like front part of the train, okay, caboose is the end. I don't know what the front part's called, but that's still got to travel. So that's pretty reasonable, I think, in the context of this question. S, we saw at the bottom of the computer output, on average predicted fuel consumption varies from actual fuel consumption by about 4.361 units per mile. I guess that sounds right to me. We saw how close all of the points were on that scatter plot, so it makes sense that they should have a relatively low standard deviation of the residuals. Their R squared was given to us as 96.7, meaning that 96.7% of the variation in fuel consumption can be explained by its linear relationship with the number of rail cars. And of course, what we learned back in lesson 2.4, what two pieces reveal that a linear model is appropriate. In a scatter, we want a pattern and we want random residuals. So we have a fairly linear pattern in the scatter plot and no evident pattern in the residual plot. I forgot my context of the number of rail cars and fuel consumption. All right. Would it be appropriate to use this model to predict the fuel consumption of a train with 65 rail cars? And lastly, here's another unusual point, 30 and 120. So I'm actually going to go back to the graphs here, just so we can analyze this information. So I know I have an unusual point here at 30 and 120, so that's my added point, and then I'm looking here at 65. Well, if we look at the domain or the range values of our number of rail cars, because it says two quantitative variables, so that gets confusing because we typically say domain is X, range is Y, but these are both quantitative variables. So the range of X values, the domain of the X values, is here in between 20 and 50. So 65 is going to be probably, if 60 is right here, then 65's got to be like way over yonder. That is definitely way outside of our domain. So no, it would not be appropriate to use our model to predict fuel consumption for a train with 65 rail cars. Because, or since, this value falls outside of our typical range of number of rail cars used to construct this model. Using such a prediction would result in extrapolation, right? I'm not quite sure if my data holds true for 65 because I only collected data on the number of rail cars between 20 and 50. And then lastly, what type of unusual point is a train with 30 rail cars and 120 units per mile of fuel consumption? Well, if my linear regression, right, if my LSRL probably looks something like that, and then I compare this here, it's kind of the furthest away, the longest distance away, those EST words. This is going to be an outlier because it's a departure from that linear pattern and it's the furthest away. It has the largest residual that I can see here just based on the scatter plot. So that point would be considered an outlier because it has a large residual value, or more specifically, not just a large residual value, but the largest residual value. So I'll go ahead and put those interpretations there so you can see them. But just as long as you answer the question, you're including context, and you are explaining what's happening. So, and that explanation is going to come from knowing the terms and using the vocabulary that we've learned in class. So, you have all the tools now to complete your study of linear regression for this AP statistics course. There are so many more fun things to do with this, and hopefully in undergrad you'll take a class that like opens your mind to the worlds of predictions. But there's one bonus lesson on transforming nonlinear data. It is not super evident or not as important for the AP statistics exam. There are a few key things that we need to take away from it. But for the most part, we're looking to have a strong linear model, and then of course the direction depends on the scatter plot. Correlation tells us about the strength and direction of that linear association. And LSRL is the line of best fit that minimizes the sum of the error squared. From there I can interpret the slope, the y-intercept, and make predictions. Also using the LSRL model, I can now find the residual or the error between the actual minus the predicted. As long as there's no evident pattern in the residual plot and a fairly linear pattern in the scatter plot, a linear model is appropriate. We also learned about the standard deviation of the residuals as well as the coefficient of determination. We learned about 3 types of unusual points, including outliers, high leverage points, influential points, and lastly, we put it all together in this computer output. Oh, that was a mouthful, but that's basically going to wrap up our discussion here on linear regression for AP statistics. So stay tuned for next unit when we'll talk about collecting data.